So welcome everyone to the next webinar in my series on modern Java by example. Today we have a number of different topics we're going to cover, focusing on different quirks of terminal operations with Java streams and parallel streams. And we're also going to talk about encounter order. And then finally, we're going to be talking about some interesting ways to implement synchronized singletons using atomic references and volatile variables together with the double-checked locking optimization pattern. So as always, let me go ahead and share my screen, and we will be on our way. So the code that we'll be talking about today is available in a couple of different locations in my Java 8 folder. So if we go over here, first example we're going to look at is in the EX17 folder, and then we're going to look at something in EX21 and then in EX28. So that's where you can find all the code we're going to talk about. So speaking of code, here is the EX17 example. And what this does is it's going to show various problems that arise when you use Java's reduced terminal operation. And it's a subtle and somewhat tricky operation in some ways. And so we're going to talk about why it's a little bit quirky. And it's particularly quirky when you start using it with parallel streams. So let's go ahead and take a look at some of the examples. You'll see that there's a bunch of different examples we look at. Just for kicks, let me go ahead and run everything so we have a way to refer back to what the results are. Okay, so with that in mind, let's go back to the code. So we're first going to take a look at some of the issues related to the fact that there's assumptions about associativity of operations that are baked into the reduce operation. So if we peek down in here, you see what this particular test does is it goes ahead and generates 100 numbers in the range from 0 to 100, inclusive, and then it conditionally runs the tests in parallel, and it goes ahead and it does a reduction. And what it's trying to do is it's trying to do a reduction by subtracting one of the values from the next one in the stream. Now, this works when you have a sequential stream. So you can see that the sequential difference of the first 100 numbers is minus 5,049. However, when we run this with parallel streams, we get some nonsensical result. And the reason for that is that there's an assumption baked into reduce that the operations are associative, which means that something like, x minus y minus z, with x minus y being done first, followed by minus z, is the same as x minus y minus z, which of course is not the case for subtraction. It's that case for addition, and it's that case for multiplication, but it's not true for subtraction or division. So this really shows up when you use the parallel versions because there's no guarantee in the order in which things run. So this code will fail in mysterious ways if you don't use associative operations. So that's kind of commonly made mistake number one. The next one we're going to look at, it's a family of problems having to do with passing in the wrong identity values for doing sums and products. So let's go ahead and take a look at this. This is the test sum method. Again, we generate a range of values from 1 to 100. We can conditionally run these in parallel. And we're going to do reduce. This time we're going to go ahead and add. We could also do a lambda expression here. We're going to use the math add exact method reference. And then we're going to pass in the identity value. And if you go back over here to the caller, you'll see sometimes we pass in the identity of 0, which is the correct value of identity for addition. And other times we pass in the identity value of 1, which is the incorrect value for identity. And in fact, if you go ahead and look at the results, you can see that when you pass in 0, you get the results that are expected. And when you pass in 1, you get weird results, which is also to be expected, but probably not what you want. We then did the same thing with products as well as with sums. I should probably move the order around here so this comes in the right order. But basically, basically what we're doing is we're doing the product operation, except once again, we're going to pass in the right number sometimes and the wrong number other times. So the identity number for product is 1, as I'm sure you remember from your probably 4th grade arithmetic class or something like that. Whereas if you pass in a 0, of course, you're going to get strange results. So if we go ahead and do the product computations with 1, we get the right result. If we do the product computations with 0, we get very strange results. And that's, again, not unexpected, but it's not what you want. Okay, let's continue and look at some other examples. We're now going to look at a bunch of mistakes people commonly make when they use reduce, and they forget the fact that reduce expects the objects to be passed in to be immutable. So let's go ahead and take a look at the example. This is the buggy stream reduce 3 method. And what's interesting about this particular example is it works fine if you have sequential streams, but when you turn on parallel streams, it falls apart most dramatically. So what we're going to do here is we're going to make ourselves a list of words, which are basically a list of strings, and then we're going to take that list of strings and we're going to turn it into a stream, and then we're going to conditionally turn it into a parallel stream, and then we're going to go ahead and use the reduce operation. And what we're going to do is we're going to pass in the string builder call. And this will end up failing because string builder does not support immutable operations. In fact, it's an operation that can be done mutably, and it's also not thread safe. So we go ahead and give a string builder as the initial identity value of reduce, and then we pass in string builder append. And the append operation is not thread safe. So when we run this with sequential processing, we get the results we expect. Here's what the sequential processing results are, which is what we expect. But when we run it with the parallel version, then strange results occur. We just get bizarre results because everything gets munged together because the string builder is not thread safe. So don't do that. Well, what you might think is, oh, I know how to fix this problem. Instead of doing a string builder, I'll come down and I'll use a string because, of course, Java strings are immutable. Well, the problem with that is that a Java string is immutable. That's good. And so we can get the correct answer here by using essentially an empty string, and then we can go ahead and concatenate together by using the plus operation. But the problem there is that strings also do a lot of copying. So even though you get the correct results, the program will be very slow. And if you take a look at the results, you can see that the parallel reduce concat, let's see. Again, I probably didn't run it long enough to see the results, but what would happen if we ran this for a longer amount of time, collected large amounts of words, that would be slow. And the reason is because we're doing a lot of string copies. A better way to do this is to use the collect joining mechanism. So if for some strange reason you need to be able to basically collect a bunch of strings together into a final string result, rather than trying to use reduce, which is either going to be buggy if you don't use an immutable object, or slow if you use an immutable object like a string. Instead, you can simply use the collect operation instead of reduce and use the joining collector. And the joining collector, as the name implies, just collects all the results and essentially appends them at the end. So you end up with a single string that's been appended together in an efficient way. And under the hood, it probably uses string builder or something like it under the hood, but because it's using it correctly with a non-concurrent collector, it all works properly, whereas the other versions didn't. So if you go back and look at the results, you can see that we got the right results. And we get the right results with string as well, just going to be less efficient, doesn't scale as well. Okay, so that was the first topic that I wanted to talk about. Let me stop sharing, and seems like there's a couple of questions. Why is the associativity a prerequisite for parallel streams? It's just because the order in which the operations run in parallel is not constrained. Remember, we've talked in previous lessons about the fact that when you start using parallel streams, you as a programmer don't have any control over the order in which the operations are performed. So it can do it in any order it wants. And so it's not going to follow it in a strict left to right sequence. And so as a result, the operations will be done in any order. Now that works fine if the operations are associative, which means you can do them in any order. But if the operations are not associative, then the fact that streams intentionally does not obey ordering means that we're going to get very strange results. So what operations can be done using reduce that can also be done with collect? Well, in theory, you could use a custom collector to probably do anything that you want reduce to do. It's in practice, that's mostly overkill. the main point is that reduce is intended to be used for concepts or contexts where you're going to want to have immutable objects. So things like integrals, longs, floats, ints or integers, those kinds of things. Those are all operations that work nicely with reduce. It's really meant for the arithmetic numbers, numeric numbers, integral numbers, whereas collect is really not intended for that, although you can certainly use it for those kinds of things. So in practice, if I'm doing numeric numbers, or I guess numeric numbers is a bit redundant. If I'm doing integral values like long or double or integer, then I would use reduce if I'm trying to sum them up, for example, or compute the product or whatnot. Whereas if I'm doing things that are more broad, more symbolic in nature, like strings or whatever other data types I'm working on, search results or whatnot, I would tend to use collect. You would not want to use, I guess the bottom line is don't use reduce for things other than integral numbers that are intended for use in that particular way. Does collect joining save the order? Yes, it will. It will save the order in which the streams come, in which the elements come into the stream. And if you want to have custom ordering, then what you would do is you would write your own custom collector that would have a finisher. Remember, you can have this finisher factory method, and you could have a finisher that would decide to just sort the items in descending order. Of course, if you want to do that, you're probably better off just using the sorted intermediate operation on a stream, because that does that for you. But you could have a custom collector that might do some arbitrary things with the objects that you collect in your collector, and it could annotate them or do whatever it needs to do. So the way you would get custom behavior would be to define a finisher and make that factor method available in your custom collector, and then have it do whatever it needed to do to collect the items up together in a coherent way. Okay, so that was topic number 1.